This is the first of two videos on preferential attachment models. We survey the history of network models that have a popularity reinforcement mechanism, and then we dig into the details of Price's model from the mid-1970s. We will prove that this model generates a network with a power law degree distribution. Here is the basic idea between each of these network growth models. When new vertices are added, they are more likely to attach to existing high-degree vertices than to existing low-degree vertices. With the proper parameters, this results in a power law network. This popularity dynamic goes by many names, including preferential attachment and cumulative advantage. People also refer to these models as the rich get richer models. I'll avoid this metaphor, which tacitly endorses income inequality as a natural and therefore benign state of affairs. Instead, I'll use a proverb that is a little more neutral, that success breeds success. Network growth models with a success breeds success dynamic have been discovered and rediscovered in various fields. Here are the four independent discoveries of these power laws from the 20th century. You can see that they occurred in disparate fields, and perhaps some of these researchers were ahead of their time. Barabási-Albert's preferential attachment model is one of the most important developments in the early days of network science research. Given the intense interest in real-world networks in the 1990s, their model became mainstream in a way that these previous formulations did not. In subsequent years, the connections to the previous models were uncovered. It is very valuable to note that this idea surfaces in multiple contexts over this 80-year period. This emphasizes the universality of this dynamic in complex systems. In this video, we will talk about Price's model from the 1970s. In our next video, we will see how to frame the Barabási-Albert model as a special case. We will be modeling citations between scientific papers, and this creates an acyclic digraph. The edges are directed. The arc ij exists when paper I cites paper j. And this directed network does not contain cycles because paper I can cite paper j only when paper j has already been published. Well, this was true in the 1970s before the innovation of online preprint archives, so we will continue to adhere to this restriction. Price's goal was to create a model that matched the behavior that you see in the scientific literature. Papers that are currently heavily cited tend to draw even more citations in future years, pulling further and further ahead in popularity. Here's how Price's model works. We start with a small seed of papers, and let's add C random citations from each of them just to get started. The important thing is that they all start out equally popular. Now, we start adding papers one at a time, and when a paper is added, it cites C existing papers. Sometimes it picks a completely random paper to cite. Other times, it picks a paper with probability that is proportional to its current citation count. The ratio of random links versus popularity-informed links is determined by the constants A and C. Now, we let this process run for a very long time. Price showed that in the limit, the resulting degree distribution has a tail that follows a power law exponent with alpha equals 2 plus A over C. And this means that we can tune the power law exponent by tweaking the ratio between random links and popularity-informed links. Here's an example of network growth according to Price's model. In this case, we have set both A and C equal to 1. Now, since A is equal to C, half the time we add a random link, and half the time we add a popularity-informed link. Also, since C is equal to 1, we only add one link from each new node. So, we get a tree. Our theorem says that the tail of the resulting distribution is a power law with exponent alpha is equal to 3. And if we look at these networks, we can see the characteristic collection of hubs at different scales that we expect from a power law network. So now we are going to launch into our proof that Price's model produces a power law degree distribution. To reduce the number of symbols we need to track, we are going to set A is equal to 1 for our proof. This isn't necessary, but it does lead to some simpler algebra. And furthermore, we need to keep in mind that the constant C does not have to be an integer. This is because C is the expected number of papers that we will cite. We will prove that for large K, the number of vertices of degree K is governed by a power law with alpha is equal to 2 plus 1 over C. So let's look at the growth process when there are n vertices in the network. The average out degree is C, so the total number of edges is C times n. This means that the average in degree must also be C. And another way of saying this is that n times the average degree is equal to C times n. And we will use that fact in our next calculation. So now, let's look at what happens when we add another vertex to a network of size n. Let's look at the expected number of new citations to a particular vertex I. For every edge that we add, with probability 1 over c plus 1, we add a totally random edge. So the probability that we link to vertex I is just 1 over n. And with probability c over c plus 1, we pick a vertex according to its current in degree. So the probability that we choose vertex I is k sub I, that is the in degree of vertex I, divided by c times n, the total number of edges. Simplifying, we get this expression. So the expected number of citations to vertex I when we add the n plus first vertex is equal to c times ki plus 1 divided by n times c plus 1. So now we are going to step back and take a look at the graph as a whole. We will partition the vertices according to their in degree, and then we will watch how this partition changes as we grow from having n vertices to having n plus 1 vertices. And so let's let p sub k of n denote the fraction of vertices with in degree k when there are n vertices in the network. This fraction, p sub k of n, is the number we actually care about. We want to show that these p sub k's adhere to a power law for large n. But it will also be helpful for us to talk about the number of vertices instead of the fraction of vertices. And so let's use a of nk to denote the number of these vertices. And finally, let's use capital N of nk to denote the expected number of new citations to vertices with in degree k. We can use our formula from the last slide to get an expression for capital N of nk. We know that the expected number of new links to a vertex of degree k is equal to c times k plus 1 divided by n times c plus 1. If we multiply this by the current number of degree k vertices, then we get the total number of new edges to vertices that currently have degree k. And this expression simplifies to c times k plus 1 divided by c plus 1 multiplied by p sub k of n. So now let's look at how the number of vertices with in degree k changes after we add vertex n plus 1. First, let's talk about how many vertices there are with in degree 0. Well, that's just equal to the number of vertices with in degree 0 before we added the new vertex, plus 1 for the new vertex that we just added, and then we must subtract the vertices with in degree 0 that just received a new connection. Then using our formulas from the previous slide, we get this relation between the number of vertices of degree 0 in this network of size n and the number of vertices of degree 0 in the network of size n plus 1. We get a different recurrence for vertices with in degree at least 1. But the argument is fairly similar. We have the set of vertices that had in degree k when the network had size n, plus the number of vertices that used to have degree k minus 1 and that have received an edge from this new vertex, and then we have to subtract off the degree k vertices that received an edge. And this results in the recurrence relation that you see at the bottom of the slide. So now let's take the limit as the network grows really, really large, and let's assume that the degree distribution stabilizes. This means that our limiting degree distribution satisfies the following algebraic equations, which we can simplify to having an expression for p sub 0 and an expression for p sub k where k is greater than or equal to 1. So here's our resulting recursive formula for the in degree. We can combine these together to get an explicit formula for the value of p sub k. So this is the expected fraction of nodes that have degree k in a very large network that has been created using Price's model. So let's get a sense of what this equation is saying. So we know the fraction of vertices that have in degree 0. That's just 1 plus 1 over c over 2 plus 1 over c. And if I want to find the fraction of nodes that have in degree 1, I need to multiply by 1 over 1 plus 2 plus 1 over c. And if I want to find the fraction of nodes that have degree 2, I need to multiply this whole expression by 2 over 2 plus 2 plus 1 over c. And if we continue this process, you'll see that the recursive formula we list here is actually correct. we still need to figure out what the tail of this distribution looks like. And doing that actually takes quite a bit of high-octane math. We need to use the gamma function and a Stirling approximation, and if we do that, we find that the fraction of vertices with in-degree k grows like k to the minus alpha, where alpha is equal to 2 plus 1 over c. In other words, Price's model generates an in-degree distribution with a power law tail, and we can get any power law exponent we want by using different values of c. So let's look at some examples of c and alpha. If we take c is equal to 1, then alpha will be equal to 3. And if we take c to be 2, then alpha will be equal to 2.5. And if I increase c even more, then alpha is going to get closer and closer to 2. Meanwhile, if I take c to be a small positive number, and that's okay because c is actually an expected number of edges, then I'm going to get an even larger alpha. For example, if I take c to be equal to 1/2, then alpha is equal to 4. And when we take c to be some number very near 0, our power law exponent alpha will be extremely large. In place of the argument for an arbitrary value of c, let's give a simpler argument when 1 over c is equal to a positive integer. So here is our expression for the fraction of vertices with in-degree k. What we'll do is factor both the numerator and the denominator to find values that they have in common. We will be able to cancel out these two expressions, which will give us a simpler form for p of k. We arrive at this expression, and now we reorganize a little bit so that we have a part that is constant as well as a part that depends upon k. Now we're only interested in the growth rate, so we just have to focus on the first thing. And if we expand out this denominator, and we take into account the fact that k is much, much larger than 2 or 1 over c, then this denominator is basically equal to k to the 2 plus 1 over c. And that confirms our power law tail for vertices of in-degree k. We've shown that Price's model creates a network whose tail is governed by a power law distribution. Again, our proof focused on the case that a is equal to 1, but the actual proof is the same for a generic a. The expressions just get a little more complicated. In our next video, we will talk about variations of Price's model, and in particular, we will show how to reframe preferential attachment so that it is a special case of Price's model.